This will be a brief demonstration video of the Forest Manufacturing Model 2054 vertical blade traveling table bandsaw. I have other videos that go into more of the details of this machine, so I'm just going to talk about some of the features that make this particular version special. These features, well, special, these are available to anybody who wants to specify them. The first thing you may notice, although it might be hard from your angle, is that the blade is not vertical. The blade is tilted forward by 5 degrees. So the top of the blade is leaning into the workpiece. I'll get into why that is in a moment. Other interesting features, well, it has our precision workpiece positioning fence. It'll have a digital readout mounted on here when we ship it out, but while we're messing around with it, we don't want something relatively delicate and expensive sitting here where it might get banged. So fence, digital readout. All the 2054s have pneumatic blade tensioning. I'll get to the controls in a moment. The interesting thing is this does have a powered traveling table. Most of our traveling tables use these 3-inch square tubes as the supporting and guiding elements. We basically have bearings that run alongside of them. It gives a pretty good ride. Usually good, something like an 1/8 or 1/16 of an inch over 3 to 6 feet. This machine, however, the customer wanted a little bit greater precision than that. So what we call the guide rail is precision linear round rail. And this part of the table is running on recirculating ball bearing support bearings. Very smooth, very precise, very expensive. The trick here is we just had the one rail with linear bearings. If you put this on multiple rails, you have the issue of keeping them all really precisely parallel. If it goes this way or this way, the table will bind up. By having just the one rail, precision mounted, it gives you a lot of latitude. You can't be sloppy, but it gives you a lot of latitude on positioning the other rails since they're just supporting vertical load, not trying to guide. Also, this machine has, instead of our usual toothed timing belt as the drive element, using a gear rack. So in the back, where you can't see it, there is an electric motor reduction mechanism and then a pinion gear. The pinion gear engages a gear rack mounted to the underside of the table. Advantage of this is it's very stiff. So the timing belt has the advantage of being, well, inexpensive, impervious to dust, doesn't really care that much about alignment. It'll just basically take a lot of abuse, which manufacturing environments specialize in. The gear rack is a much more mechanically rigid system, offering more precise control of the speed and positioning of the table. For delicate applications, it makes sense. The gear rack also requires a much tighter control of the position. You want that gear and the gear rack to line up nicely, so you have to precisely control the position of the table. This linear round rail allows that. So the table drive is upgraded with the precision table tracking and the gear rack drive, so you have a very precise, smooth, rigid table speed mechanism. Controls. This machine has our pneumatic blade tensioning. It's pretty much all of our big saws like this do. Pneumatic blade tensioning replaces what you normally might see as a screw over spring mechanism on a smaller saw. Those are reliable as an anvil. Everybody understands how they work. But for a big saw like this, they get really inconvenient, particularly when we're running a big blade. So we have an air cylinder in the back being used to tension the blade. It's controlled by a electric solenoid valve on the back side. Allows us to do a few things. We got built into the controls. We have a blade breakage detector, such that if you snap the blade, everything stops. If you have insufficient air pressure, it won't let you start or stops everything. And a little bit more logic baked into here. The controls on this machine are our variable controls. So of course we have a variable speed drive for the table. This machine also has a variable speed drive for the blade. I've got it set up right now to run the blade at up to 4,500 feet per minute, and you can vary that on the control panel face here. We've got a knob rheostat on the front, in addition to the other controls. So variable panel, We have an inverter controlling the table drive. We have an inverter controlling the blade. Those have faults and everything, so you have all your usual status lights. Let's see, what else interesting? Oh, the variable controls also include a remote control pendant. The advantage here is we have almost all of the controls are here on the panel face, including the important big red mushroom button. Most of the controls are duplicated on this panel, or this handheld pendant. So let me see if I can put this where you can see it. So you have saw start, saw stop, table forward, table reverse, table stop. And this machine doesn't have the laser, but you have an extra button for the laser. And importantly, on the end here, hidden inside, you have another control dial to control the table speed. What this does, if you're cutting something fussy, this allows you to walk around the saw and control all the major saw functions from this control pendant. It allows you to observe the cut and control it instead of being stuck over at a control panel like you might otherwise be. Oh, and it has an additional e-stop button that goes on a pedestal at the back of the saw. A little bit of logic baked into here. The table speed, this one is set up with a table speed maximum 4 inches per second. It has automatic stop at both ends. The way the logic is set up, what you'll normally do is you'll start the saw. It takes about 8 seconds to reach full speed. Then you will press and release the table forward button. Starts making a cut. If I stop the saw, the table stops also. I have the table forward speed here. The table return speed is on this panel face. The thinking there is when you're returning the table to home position, i.e. after you've made a cut and you're resetting for the next cut, you're almost always going to leave that table return speed at 100%. So you're probably never going to change return speed. You just hit the reverse button and it'll back the table up at the maximum speed. And when you're setting up to do a cut, start the blade motor and then start the forward button. The way the logic is set up, if the saw blade is not running, you can advance the table by pressing and holding the forward button. Release the forward button, it stops. The thinking there is we want to be able to position the table for doing setups or maintenance or whatever, or talking on a video. But when you are actually working with a workpiece, making a cut, you want to make sure the blade is running before you advance the workpiece. You don't want to ram the workpiece into the blade if the blade isn't running. You might damage the workpiece or your blade. So the logic suggests that you start the saw blade motor and then start the table forward. Once the saw is running, press and release the forward button, it'll go forward until you press stop or it reaches the end of travel. That's the basics of the controls. All the rest of the features are covered in other videos. So what are we cutting today? Why have I tilted this blade forward by 5 degrees? The customer for this saw, and I actually have many other customers cutting this material, is cutting a honeycomb material. Comes in a lot of different types. This table is actually set up to cut through up to a 10-foot long workpiece. So the 120 inches, the actual table travel is 11 foot to allow you to cut through a 10-foot workpiece with a little bit of excess on both ends. The honeycomb material comes in a couple different flavors. It comes in like phenolic plastic impregnated craft paper, it comes in Nomex, and it comes in aluminum. There's also more exotic stuff. There's fiberglass, there's carbon fiber honeycomb, but we don't get into that too much here. So this is a sample I've already cut off, but let's see if I can get this to see on the camera there. But it's a hollow honeycomb cross section. And the customer, lots of customers have large sheets of this stuff that they want to cut into smaller pieces. So it's sitting on the table like this, and the blades pass through like this. Now the idea behind having the blade tilted is if the blade is, my finger's the blade, pretend please. If the blade is moving like this vertically, as it cuts through these cells, the blade is seeing a solid wall of material, then nothing, then a solid wall of material, then nothing. And so it can lead to a weird jaggedy cut. By tilting the blade forward 5 degrees as it cuts, it's cutting through lots of little thin sheets at a bit of an angle. Instead of just hitting solid material, nothing, solid material, nothing, by sweeping it through at a bit of an angle, we get a smoother cut on the material. I'm using gloves right now. This aluminum that I'm working with today is kind of the worst case of materials to cut. It is metal, and I'm using a metal bandsaw to cut it. The blade I'm using right now is one option. This blade is what's called a honeycomb style blade. It basically has teeth, but the teeth are sharpened like a knife. So it's actually peeling away material with a knife cut, and it's also cutting out a channel of material. It's a very expensive blade. It works great on the phenolic material, phenolic craft, the no mix time materials. It's doing okay cutting this material, but I'm cutting metal with metal, and the blade is going to get dull relatively quickly. I've made maybe 10, 12 cuts with this blade so far, and it's not noticeably going dull yet, but it's not going to last it's not going to last for weeks of this. So my first cuts here, I'm using this honeycomb style blade. I'll also use later on, not in this video, a 1-inch wide blade with regular teeth, but lots of small teeth, probably 10 teeth per inch, maybe 14 teeth per inch, lots of small teeth. So I do have a workpiece here to play with, a larger piece. This is relatively dense and heavy. There we go. My understanding is as these type materials go, this is a relatively high density material. Heavy wall, small cells. So it's kind of the worst case for this application. As I mentioned, we do have a workpiece positioning fence here to set the distance from the blade to your reference surface. I'm using right now just some magnets as positioning tools. So I've got a couple magnets here to position off of. One thing that's funny about this material to cut is you want to kind of push it in. It's very lightweight. It'll slide all over the table unless you lock it in. So I've been using magnets to lock it in. I got this material from another customer, a different customer, and the edge cuts on it are all kinds of crooked, wavy. So my first instinct is to use something like this magnetic positioning fence, which is nice and flat, and push up against the workpiece. Well, the workpiece here isn't flat, so I'm just pushing on a point. If I push in, I'm distorting the workpiece. So I've been looking at other, by the way, this is a really cool tool. You can get this from us. It has switchable magnets. So you put it where you want it, flip the switches, and it locks to the steel table. Release the magnets, and it moves around pretty easily. If I just push up against the workpiece though, I don't have a flat reference surface here, and the material is a little bit squishy. So I try to push it in, it squishes, and weird things happen. I don't have an answer for this yet. But for now, just for the sake of the video, I'll use this to keep it up against the positioning fence. Test cut. So I'm still being fairly conservative with how quickly I can cut this material. I have found out that if I run really, really fast, like full speed, I will not get a straight cut. I am, after all, cutting a big piece of metal. So if I push too hard, the blade will try to deflect a little bit and get a crooked cut. So I'm running a fairly conservative blade speed. It's probably something like 0.4 inches per second, maybe a little slower. I am running full blade speed. No, pardon me. So I'm not sure if I said blade or table. Blade speed, I'm running full speed, 4,500 feet per minute. Table speed, I'm running pretty conservatively at something like 0.35 to 0.4 inches per second, so relatively slow. So I'll knock out a cut for you here real quick and show you how this thing is useful. So I've actually got, the blade is like 12 inches from the workpiece back there. Start the saw up. It takes about 8 seconds to hit full speed. That's just a limitation of the inverter. What I usually do, by way of being extra cautious, is I set the table advance speed at 0, hit the forward button, then I can increase the speed of the table. Then I'll go a little fast here to advance the workpiece up to the blade. Then I'm going to slow down. I'm actually going a little faster than I thought I would there. And I mentioned that there is some concern about using a metal blade to cut metal and going too fast. I have actually seen sparks in my earlier test cuts from the blade cutting this material. So I know I'm eroding the blade more quickly than is ideal, but this is a worst case material, and it might be a better candidate for a hook tooth style blade instead of this special honeycomb style blade. So I'm gonna go ahead and stop it. I broke my blade. That's pretty nice. See if I can show this up. So my cut surface, pretty nice and flat. Interesting thing is, if you just, I don't know if you'll be able to see this looking down here, if you just sight down the honeycomb, the cells are not all in a straight line. The cells do some of this. The cells are not in a straight line. There's something like an 1/8 or 1/4 inch of, just in this length of this workpiece, there's something like an 1/8 or 1/4 inch of wiggle in the cells. They're not all in a straight line. So we're trying to square up something here that doesn't really want to be square. But except for breaking my blade there, I think we're doing pretty good. So we're going to do a second set of videos here using the hook tooth style blade. But if you have any questions or like to discuss a specific application, please feel free to call or email me. Thank you for your time.